Let's have a quick review of our vector addition using component method. In your previous videos, it's commonly given the magnitude of a vector and its direction. Example, given vector A, 3 units, then directed 30 degrees north of east. But in here, I want you to look into a different given. In here, you are given the components, directly the component. Sample AX. AX, how many units? So it's about 1, 2, 3. So 3 units. How about AY? The AY is equal to 1, 2. So that's 2 units. Okay. So my question, is vector A now equal to AX plus AY? Is this correct? Nope. Why? Because AX and AY are just lengths of the projection of our vector A along X and Y axis. This AX and AY are not vectors. Therefore, you cannot add two non-vectors to give you a vector quantity. So you need to add vectors to have a resultant vector. So AX is 3 units plus AY 2 units. That's 5 units. So it's not equal to our vector A. So how to express our vectors in terms of vector components? So in here, that's the reason why the unit vector introduced. What is a unit vector? Dimensionless vectors. Or in other words, unit vector are unitless vector. Why unitless? Because this unit vector, sample unit vectors, the I hat, j hat, and k hat. These sample vectors are vectors with magnitude of 1. And then what's the function of this unit vector? Just to give us an arbitrary direction. So commonly used directions for unit vectors are the I hat for x-axis, the j hat for y-axis, and the k hat for the z-axis in our three-dimensional. So let's now proceed. So vector A, therefore, can be expressed in terms of its vector components now. So it's equal to AX I hat plus AY j hat plus AZ k hat. So basing on our example, we only have two dimensions. So A therefore is equal to, since we don't have the z-axis, so we only have 3 I hat plus 2 j hat. Now we have in here expressed our vector in terms of its vector components. The 3 refers to the magnitude of our vector component along x-axis, I hat, and 2 units for our y-axis, or the component of this vector A along y-axis. Let's determine now the magnitude of our vector A. So what is our A now in terms of its magnitude and the angle, or theta A? So let's label this as theta A. So what is the magnitude? If components are given, just the reverse process of your previous example, that if this two are given, the magnitude and direction, we compute um, the components, the 3 units and 2 units, using the SOHCAHTOA. In reverse, the same. So let's now we can now compute the magnitude of a vector A, this length, using the rectangular components. So in here we can see that this is right triangle. So right triangle. So if it is a right triangle, then the Pythagorean theorem applies. And we can use a Pythagorean theorem. So we can we can compute our magnitude as our c square, or the longer side, equal to the square root of these two sides forming right angle. So this is ax square plus ay square. So, or this is equal to the square root of 3 squared plus 2 squared, and that is equal to 3.6 units. So this is now our magnitude. How about the angle, theta A? So since we have the opposite and adjacent to our um, angle theta, or theta A, we can use the inverse tan, or TOA, the tangent inverse of this opposite over adjacent. This is equal to 2 over 3. Then our theta A is equal to 33.7 degrees. Thus, our A, given the magnitude, is equal to 3.6 units, 33.7 degrees north of east. Okay, this is now the expression using magnitude and direction to define our given vector A. And this is also the expression A is equal to 3i hat plus 2j hat in defining vector A using vector components. So you can use the same, you can apply the same concept in determining the components of other vectors. Example, in our vector B, this is our bx and our by. Bx 1 unit, then by 1, 2, 3, so 4 units. Okay, so why all positive, though it is in the negative or a negative quadrant for the along x-axis? Let's just use a positive in here because the bx and by are simply lengths of our the projection of vector b along x and y axis, not yet vector expression or vector component. But if we are to write vector b in terms of its vector components, then vector b is equal to negative I hat plus 4j hat. Okay, so let's have vector c. So vector c is in here, cx for along x-axis and cy for the y component of our vector c. So again, our cx is equal to 1, 2, 3. So 3 units. and our cy is equal to 1 unit. But in writing our vector c in terms of vector components, this is equal to negative 3i hat minus j hat. So 1 unit. So we have in here sample expression or expressing our vectors using vector components. So if you want to determine the magnitude of a vector B, just do the computation, the same as what we have done with in finding the magnitude of our vector A. So using the Pythagorean theorem, and also in our vector C to determine this length using Pythagorean theorem, and the angle the same, applying the SOHCAHTOA or the tangent inverse in determining the angle theta B and theta C, okay, respectively. Now let's continue. We did not add anything yet. So this time, let's add using our component method. Expressing a vector A in terms of components, this is equal to 3 I hat plus 2 j hat, and our vector B, negative I hat plus 4 j hat, and for vector C, this is equal to negative 3 I hat minus j hat. Then how about how to compute our vector A plus B plus C? Or let's consider first two vectors. Let's add two vectors at a time. RAB, the resultant vector A plus B. So let's just add simple arithmetic of the vectors or the components along the same direction. So this is just simply grouping. So the AX plus BX all along I hat. So that we can just add automatically, plus AY plus by along j hat. In this case, you have 3 minus 1 plus 2 plus 4 j hat. Therefore, your resultant vector is just 2i plus 6j hat. So this is our vector RAB. Our vector RAB, that's 2 units along x-axis, so 1, 2, and then 6 units along j. So that's 1, 2, 1, 2, 3, 4, 5, 6. So as you can see, if our vector RAB or the resultant vector of our vector A and plus B, or the RAB, using parallelogram. So for checking, we can see that if we are to draw the parallel of vector A from the head of B, so this one is, and then the intersection also of the parallel of our vector B from the head drawn from the head of our vector A is this one. So their common point of intersection still the same, the head of our vector RAB in terms of resultant using component method. Okay, so how about the resultant vector using component method of the three vectors now? So resultant vector is equal to A plus B plus C. So in here, our vector R is equal to So just quick review, or just 3 minus 1 minus 3 I hat plus 2 plus 4 minus 1 j hat. So this is equal to negative I hat plus 5 j hat. So where is our r located now? The resultant of the 3. Let's choose this one. Okay. So negative 1, so in here, negative 1, and then positive 5. So 1, 2, 3, 4, 5. So this is where the head of our resultant vector located. So a resultant vector, the a plus b plus c, is this. So the resultant vector is now r. This is equal to a plus b plus c. And their angle is theta r. So we have the magnitude. What's the magnitude of our r? So again, so this is, we can apply the all the ry squared. Our rx, by the way, are these values. This is equal to the summation of all the rx and all the y along y-axis direction or components. So this is equal to negative 1 squared plus 5 squared. This is equal to approximately equal to 5.1 units. How about theta r? Again, using the tangent inverse of the opposite side of our resultant, that's the ry over rx, or this is tangent inverse of positive 5, or the 5 over negative 1. So this is equal to negative 78.7 degrees. Okay, why negative? So let's check our resultant vector located in the second quadrant. So what makes this negative? Located along negative x-axis, but then positive y-axis. So therefore, the resultant is equal to 5.1 units, 78.7 degrees located north of west. So this is now our resultant vector using component method.